Good morning, everyone. Thank you, Professor Majumdar, for this opportunity. And for all the participants, it's so good to have this workshop going on for celebration of a decade of Higgs discovery. And today we have three talks, excellent talks lined up in the morning session. First up, we have talk by Professor Kirti Ranjan. Let me just briefly introduce today's first speaker for you. Professor Kirti Ranjan is a faculty at Delhi University. He has been working on various aspects of experimental high energy physics since 1998. As part of his PhD thesis, which he did from University of Delhi, he worked on the development of silicon sensors for the pre-shard detector of the CMS experiment. He joined BU, Physics Department of Delhi University in 2007. And as I said, he's currently a professor there. Besides his current association with the CMS experiment, he's also involved in our T50 collaboration on radiation-hard silicon detectors. He was associated with the D0 experiment at Tevatron, Fermilab US, and proposed the International Linear Collider. And I'm actually especially happy that he's my colleague in CMS and we are in the same CMS tracker upgrade group. Thank you, Kirti, for agreeing to give this talk. Please start.
Yep. Okay, thank you, Seema, for the nice introduction. And I would like to start by thanking Kajari for inviting me to give this talk. I mean, the topic of the talk is clear. It is the Indian contributions, which is those enthusiasts or those analysts who work with affiliation from Indian Institute. So Indian contributions in the standard model Higgs boson search. So I'll keep my talk limited to the standard model Higgs boson search because there are other talks on the beyond standard model search from Run1 and Run2 data, and also the standard model Higgs boson search from Run2 data. So, I mean, while collecting, compiling and collating the information from various analysts, it was just bringing back the nostalgic feelings, the one which we had when the LHC started, the one which we had when this discovery was getting announced. So it was nice to actually compile all of that here in this talk. Again, I mean, I would like to thank TFR for actually having this symposium on celebrating a decade of the Higgs boson discovery. Okay, so I could have skipped this slide completely in view of the excellent reviews by Rohini and Vivek on the first session on first day, but I just wanted to do it for the sake of completeness of the talk and also to set the stage for the analysis. So let's just try to figure out what was the standard model Higgs boson status before Run1 or before Run1, which was just starting. So there were theoretical limits on the mass of the Higgs. Remember, this is the free parameter of the theory. So there were limits from the unitarity arguments. And then, of course, there were theory limits also from the vacuum stability and the triviality ones. The indirect constraints came because once you introduce a standard model Higgs boson in the theory, its virtual excitations, of course, contribute to the various electroweak processes. I mean, the observables, for example, the mass of the W boson, mass of the top quark, and so on and so forth. So one can actually try to fit the electroweak data and check the constraint on the Higgs mass, which around that time was actually getting constrained to around 158 GeV or 160 GeV. And then there were the direct experimental limits. Remember the left limit from the almost the kinematic reach of the experiment, putting the Higgs mass 114.4 GeV at 95% confidence level. And then there was Tevatron, which was running with PP bar collisions. I am showing here a plot which is from 7th March 2011, just before Run1. Of course, Tevatron updated this result later on with 10 femto-1 inverse also. Now, the important point is I will be showing this plot time and again. Professor Kyle Cranmer gave an excellent talk and a very enthusiastic talk on the statistical limits setting in the case of Higgs boson or the discovery potential, how we exploit that. But just for the sake of completeness again, I mean, what is shown here is the median expected limit shown in the dotted curve and the observed limit, which is shown in the solid black curve, for the Higgs boson production cross section times the branching ratio and normalized to the standard model cross section as the function of the Higgs mass. So line at 1 is very important. The green and the yellow band, of course, are the standard, one standard deviation variation from the median expected limit. And as I said, that this SM equal to 1 becomes important because whenever the expected and the observed limit basically goes down, that we start thinking about the exclusion, or we start thinking about the upper limit on the cross-section times branching ratio. So as I have mentioned, Tevatron put the limit of 158 to 173 GeV, and those of you who were associated with the experiment or otherwise also, Tevatron actually tried to look for the associated production in the low mass, and only in the high mass regime it was looking at the glue into Higgs and then decaying to WW. Now, what is the luminosity which I am going to talk about? The luminosity for Run1, almost everybody by this time knows, was around 5 femtobarn inverse, and shown are the plots of the total integrated luminosity evolution with time. Some of you, I mean, they may be interested in looking at the dates where the Tevatron started taking, LSC started taking data from 13th March 2011, and the first run continued till 30th October. Remember that whole of the discovery and these analyses were made possible because of the excellent running of the LSC during its initial years. And LSC really delivered. And of course, the experiment also, the detector group, which ensured that the data taking was very good. The recorded data was also very nice. And for ATV analysis, basically, center of mass energy of analysis, we have this 19.7 femtobarn inverse of the data. So this is basically the luminosity, which I am going to talk about in my subsequent slides. Now, again, the standard model Higgs production, as we know, it takes place using gluon fusion, which is basically the dominant production mode in the entire Higgs mass range. The contributions are also coming from the vector boson fusion, associated production with W and Z, and associated production with TT bar. And we can see that the production cross-section is approximately an order of magnitude lower even for VBF, but there are characteristic signatures such that, for example, in the VBF vector boson fusion, one can see that there are two jets which are having a large rapidity gap separation and then high invariant mass. In the case of associated production with W or Z, we have a standard handle coming from the W and Z, which can help in reducing the background. So that means that even though the cross sections are less, but we can still utilize these channels. And the decay mode picture, of course, is quite busy. But in the low mass range, I mean, something like less than 130 GeV or so, it is the Higgs boson decay mainly to fermions. Of course, the gamma gamma is also the golden channel. And then in the intermediate mass range, it is the decay to massive vector bosons, the WW and the ZZ, which were important. And once the TT bar channel gets open, I mean, of course, the decay probability is there in that as well. So now with this stage being set, this is what I want to present in the talk, the main points. Now, this is the only slide where I am listing the institute's name. I am not going to list the names of the institute afterwards. I, of course, looked at the analysis which we have done. I tried to compile it, but in case if I am missing something, I would be gladly, taking that also and then update the slides and again upload it just for the sake of reference. And I am apologizing to those people in case if I am missing something in advance. So let's just look at the analysis. For example, Higgs to ZZ to 4L. This is the analysis which was done for the early low luminosity. Remember, this is the golden channel with 2E, 2 mu, or the 4 mu or the 4E ones. Later on, the DU group shifted to this ZZ to 2L2 nu. If you look at the branching ratio, that it has more branching ratio than 4L in the high mass regime or otherwise also. But of course, it is suffering from the poor resolution of the transverse, missing transverse momentum. And then the 2L2 tau analysis, which was done to complement this 4L analysis. Tau reconstruction is not that easy, so mass resolution is poorer, of course. Then in the Higgs to WW sector, the analysis was the analysts contributed or participated in this L nu JJ1, which is of course having the highest branching ratio here, but at the same time with very large background. Then the analyses were also performed in the associated production of the Higgs. In most of these channels, the one which I have described above, the VBF is vector boson fusions are also included. But then there are separate analyses for the associated production of Higgs with the with W bosons, where the Higgs subsequently decays to WW or tau-tau pair. Then there is this invisible Higgs analysis. In principle, this is non-standard model decay of the Higgs boson. I will comment on that. And once the Higgs boson was discovered, the properties of the Higgs boson were also studied. For example, constraining Higgs boson width using ZZ and the WW channel, combination to give the Higgs mass and the coupling, etc. And also a very interesting one, the differential measurement of the Higgs cross-section with the luminosity, which I already mentioned. So this slide basically tries to summarize the institute's contribution to various aspects. And as you can see, the Indian groups participated in very lively manner in almost all the channels. So what I'm going to do now is to just give you a flavor of the analysis. I mean, it is more like a teaser, and I am basically keeping the reference here so one can look at those references. I am keeping the reference only for the physics analysis summary and the, of course, publication. So all of these are public documents anyway. So let's just look at this particular slide, which is the only slide which I have, not for Run1 data, but just before that. There were many such contributions, to be honest, before that as well. The reason why I kept this slide is because this is the way actually the university or the group entered into this 4L analysis. Now, this was the search strategy for the Higgs boson in the ZZ decay channel, the golden mode 4E, 4 mu, 2E, 2 mu. With the, of course, the background coming from the irreducible ZZ continuum, and then the reducible components coming from ZB bar and TT bar, W plus jets, Z plus jets, and the multi-jets, of course. Now, where the group actually contributed, I know because we worked on it, and some of our colleagues were also there, that it was on the isolation and the impact parameter. Now we know that for the leptons coming from 1Z, it is important. But the interesting aspect for the Higgs was that the another Z, which was coming and also giving the leptons, the two leptons, which we are going to study, if you tune your isolation and impact parameter significance properly, then you can take care of several backgrounds like ZB bar, TT bar, Z plus jets, and so on and so forth, where the jets are misidentified as the lepton. So this was the main contribution, but then one can look at the lepton PT reach, which was as low as 5 GeV for the fourth lepton. And then, yeah, I mean, the analysis was supposed to have consistency with the Z mass, one on shell and another with off shell. On the right is shown basically the 4 lepton plot, invariant mass plot for 2E2 mu channel. And as you can see, it is the ZZ continuum, which is basically the main background here after the selection. Yeah. And okay, so the two things which were there, I mean, this is, remember, it is the projection. The projection was that if one femtobarn inverse of the luminosity taken from the LSC would be able to exclude, I mean, Higgs, in case if it is not there, in the highest mass region, about 185 GeV onwards from this channel itself. And in fact, at that time, there was a discussion on the 10 TeV run of the center of mass, at the center of mass energy of 10 TeV. So the projection was also done there. And of course, it was combined with the WW channel. So these were the exclusion limit which was given for the projected 1 femtobarn inverse. Now, the work continued for the lower integrated luminosities of 1.13 femtobarn inverse and 1.66 femtobarn inverse in the golden mode, that 4E, 4 mu, and 2E2 mu. The Higgs mass range was scanned from 110 GeV to 600 GeV. I won't, of course, say anything about the signal backgrounds, which I have already mentioned. Data was triggered using single lepton trigger only in the initial portion, but it was mostly the dilepton trigger because we already have Z decaying to dilepton. The baseline event selection was very clear, clean, because it is one of the cleanest channel. So you have to first construct the Z, the on-shell one, with the well-identified isolated leptons of same flavor, opposite charge. Then there was this 3 leptons portion, which was in the second step to take care of the WZ kind of a diboson background. Then the 4 leptons were selected. The PT limit was already mentioned to you. And the 4L candidate, basically the 4L invariant mass, was constructed with a mass greater than 100 in GeV. As I already mentioned, the work mainly focused on the isolation, relative isolation of the 3rd and the 4th lepton, and also the impact parameter significance for each of the lepton. The baseline version of the analysis had, of course, one on-shell Z boson, and another one which is the offline, for which the mass range was taken from 20 to 120 GeV. And at this early version of the analysis, both 1.13 femto1 and 1.66 femto1 inverse, all the backgrounds, major backgrounds, were done using the data-driven background estimation. But it was interesting to note that ZZ, for example, was not done from the side bands, but was done from the Z to dilepton decays, of course, accounting for the cross sections and the acceptances. And ZBB bar and TT bar, for example, was done by inverting the impact parameter significance. Z plus jets, where the jets are misidentified as leptons, were done using the like charge, same flavor leptons. So this was quite good. Even in the early stages, it was almost, not almost, completely data-driven background for most of these. And this was the 4 lepton plot for 1.13 femto1 inverse. Now, if you look into this table, which was the event distribution, it is the ZZ continuum background, which was dominating almost everywhere. And observed events were 15, which was consistent with the background, 14.4. But the interesting thing was taking place here. If you look at the 4 lepton invariant mass of less than 180 GeV, then there were 6 events which were observed, whereas the expected background was 1.9. So the probability for the background to fluctuate at least as large as 6 events turned out to be 1.3% at that time. And of course, in the absence of any axis, the exclusion limit was put to be 1 to 2 times the expected standard model cross section, almost in the entire range from 180 to 450 GeV. So, it was good to see that whatever was projected earlier could be realized in the almost the 1 femto1 inverse of the analysis of the data. As a side one, the spin-off, you can see that the ZZ cross-section was also measured, 17.5 femto1 with large statistical uncertainty. Of course, within the uncertainties, it was consistent with the standard model. Now, on this is the next slide, which is basically the same slides earlier, except that the data was updated to 1.66 femto1 inverse. There was excitement for doing analysis with the data, and hence there were public analysis summaries. So physics analysis summaries coming so often, actually in the initial stages. So what I would say that overall the 21 events were observed, which were of course consistent with the standard model, all background projection. But those 6 events remained there, and in the additional data, there was no event added into this 180 GeV. The background of expected background turned out to be 2.8, and the p-value turned out to be 6.5% for this version of the analysis. After that, the group actually migrated to this 2L2 new channel. And remember that what was happening around that time with the excitement that, okay, since we have to cover the whole phase space, so all these channels or decay modes have to be covered. Now, I have listed here almost all the passes and the publications which are done from this analysis, but that is just to tell you that the analyst got involved from the very early stages of this channel, and then continued with almost all the data, not almost all the data. In fact, there was this boosted decision tree analysis, which was done only for the CMS thesis endorsement, but that was also done in this one. So essential features, if I look into that, it's a high mass Higgs search channel. So it was done for the 200 to 1 TeV. Branching ratio is higher, but of course at the expense of worse resolution. Since we cannot reconstruct the Higgs boson completely because of the presence of these neutrino. So in this one, the MT of the dilepton and the transverse missing energy was used. So MT is used as the discriminating variable, the final one, on the basis of which the limits were placed. Double lepton triggers, and then there were some additional data sets for background estimation. Now, I wouldn't go into the pre-selection, etc. It is basically a lepton selection which has to be consistent. So, I mean, with the Z boson selection for on-shell one. And then the third lepton V2 to take care of the di boson, anti-B tagging, and soft muon V2. At that time, this was the jet probability tagger, which was used in this version of the analysis to take care of the TT bar in the single top and ZBB background. Then there was this minimum delta phi of the jet and the transverse missing energy to take care of the misreconstructed jets coming from this Z plus jet events. So basically, it was also very clean pre-selection, to be honest. And then the events were categorized further on the VBF. And as I mentioned earlier, we are requiring 2 non-BTEC jets with, of course, high PT jets, I mean, greater than 30 GeV jets with large rapidity separation, high invariant mass. Dileptons even should be there between those jets. But then there should not be any central jet. There is no jet. There should not be any jet activity. And for the remaining 0 jet and the greater than equal to 1 jet event, it was the transverse missing energy and the transverse missing energy and the empty cut which were used ultimately for discriminating signal from background as well as for placing limits. Now, this was also one of the channel in which there was problem from the MC-based background estimation because of this misreconstructed jets being giving the major chunk there. On the right-hand side, it was just the event flow. Remember the talk from Vivek where he showed that how the individual selection, event selection gives you more and more power in terms of selecting your signal over background. Now, the data-driven background was mostly done from the, for the 2 ones, for Z plus jet, it was from the gamma plus jet having larger statistics and similar kinematics. Of course, it was reweighted for the PT distribution number of primary vertices. And for the non-resonant background estimations, EMU sample came handy, and it was scaled by the scale factors which were determined from the sidebands. There also the major backgrounds were done using data-driven, and the transverse missing energy that looks quite in good agreement between data and the not the data, but using the data-driven background. So these are the 3 plots: the transverse mass of the Higgs or the dilepton in the transverse missing energy in the 0 jet and greater than equal to 1 jet system, and it is the missing ET in the VBF1, which ultimately gave in the absence of X's, gave upper limits on the production cross-section times the branching fraction. Important to see that even the expected limit you can see with the whole of the data, of course, was from around 265 GeV to 761 GeV for the cut-based analysis, and when the shape-based one were used, it was up to 900 GeV. So this channel was able to exclude basically Higgs boson, high mass Higgs boson in the entire mass range, and I will show the combination also. Now, this slide I'm not going to actually discuss. It is just the evolution of the limits in this channel, going from very low luminosities as the luminosity increased, and how the exclusion took place from, the expected is the one which you can look at, even the observed one, of course, just how it evolved with luminosity. Very good, nice one to compile, actually. So, this slide is actually just to show that even at the early stages, the group understood the importance of the multivariate analysis. And so with some changes in the baseline analysis, of course, relaxing the cuts and given input variables which are relevant for this ZZ2L2 new ones. And after doing all the overtraining checks, looking at the correlations, reverse ranking, etc., the discriminant was made. Here it is showed for 400 GeV, but it was done for all the mass range. and limits were also imposed on the basis of this BDT discriminant in this channel, but this was only for the thesis endorsement. Remember, the same analysts were also very active in the original searches in the cut count and the shape-based ones. The limit was slightly better, which means that the shape-based analysis was able to do almost all the justice to this high mass region. Now, this is another analysis where which was not easy because Higgs to ZZ, one Z decays to dileptons as usual, but another Z decaying to di tau pairs. This was also not an easy analysis because we were supposed to reconstruct taus here. And because of this, in fact, I find that the group also contributed in the reconstruction of the tau leptons. So again, just to show that the group got involved from the beginning and continued the searches till the full luminosity, all the references and the public, all the references, the public document and the publications are listed. Just to give you an idea that initially the publication was done for almost all the 7 TV data. Next publication, which was there, was done for the data which came from the discovery time. I mean, remember the 5M1 was 7 TV and 8 TV. And the final one, which is basically taking care of entire one. Now, backgrounds are basically similar, except that the composition is such that now the fakes contribution can even go bigger. So one has to come up with the idea of first the tau reconstruction and then the way of controlling the background. So this analysis had one Z, of course, the dilepton pairs, another Z where the hadronic decaying, electronic decay, and muonic decay tau were also considered. It complemented 4L search, the ones which I mentioned earlier. So there were no, for example, tau E analysis or the tau mu analysis. But okay. Then the pre-selection, if you look into it, it is dilepton trigger. Of course, you have to have dileptons consistent with the Z, which was on which is on shell, the isolation and the Z boson selection. Next was the Z2. Here, the lepton selection, where the leptons are coming from the tau decays or the hadronic decays of the taus. So tau was reconstructed using hadron plus strip technique. And of course, to control the background here, you have to have tightened isolation on electron muon. The visible mass was constrained between 30 and 80 GeV for tau mode, just to ensure to remove this Z to LL background for this channel. And then there is this 90 GeV for tau E tau mu, because this is E mu channel, and hence in principle should not be seeing those many Z to LL events which have the same flavor ones. And then there were delta R cuts. All major background were data driven. Again, just like the 4L channel, the ZZ, for example, was done from the Z, inclusive Z. And then for estimating the jets reconstructed as the taus, you have isolation, relaxation, you have same charge relaxation. And then you try to see how many of those misidentified jets can actually sneak into the signal. So that's also a good one. And in fact, the plot which is shown now on the bottom is the 4 lepton, in fact, the LL tau tau plot. And you can see it is the ZZ with the Z plus jets, which basically make the major contribution. Now, here are listed all the 8 channels. In what is important to see that there were 10 events which were observed. Total background expected was 11.6. So basically it was consistent with so observed one was consistent with the background. On the right side, which has come just now, I just showed the same now with higher luminosity, where the 7 and the 8 TV ones were added. And again, I mean, you can see the consistency between the all background and the observed one in, of course, the high mass range. Remember, this is the high mass range analysis. And then I have a plot from all data as well. Now I am showing here 2 limits, and the final one will be shown in the combination. The one on the left-hand side is the earliest one, 4.7 Fem to 1 inverse. So there was this 95% upper confidence limit on the cross-section times branching ratio, which was 4 times to 12 times. So you can see the amount of work which must have gone into reaching up to this point. And the analysis was sensitive in the region. And also, again, it complemented it. It also improved the sensitivity of the 4-lepton analysis. So on the right hand side, I'm just showing a plot, again, the same plot with the 4-lepton combination for the luminosity, which was the discovery luminosity, if I can say that. And it was able to reject basically almost all the high mass region. So this was 2 tau analysis, which was also very useful in complementing 4L channel in basically putting limits on entire high mass range. So another one, Higgs to WW. This time one of the W decaying leptonically, another W decaying into jets. Hence it is suffered from the major background from W plus jets kind of events. So references are listed. Mass range in which this analysis was done was from 170 to 600 GeV, so another high mass analysis. So backgrounds, of course, here comes, it's dominantly from the W plus jets, Z plus jets, QCD multi-jet, and the other ones, the residual ones coming from the TT bar, single top, etc. Now, without going into the event selection, it is the lepton and the missing ET which you have to do for selecting one W. You take care of anti-betaing to take care of the TT bar background. Then you have this delta phi cut again to take care of the Z plus jet kind of background. Transverse mass coming from the W greater than 30 GeV. What was interesting in this analysis was that a new PZ, the neutrino in general is unmeasurable, right? So a kinematic fit was performed to constrain, to basically get the idea of this PZ of the neutrino by constraining the L nu pair mass to be consistent with MW and also the dijet's mass to be consistent with MW. Now, this actually improves the dijet mass resolution actually in this channel, which is basically on the top left. But this can also help you basically getting the complete kinematics out of the Higgs decay. And hence a likelihood discriminant was also made to distinguish Higgs signal from W plus jets using the input variables which had 4 of the decay angles and another lepton charge. Remember the W plus W minus asymmetric charge distribution in the, just the WW events, whereas the Higgs to WW, it's symmetric. So with this, discriminant was made actually to discriminate between the signal and the background. What is the next was to do first the unwind maximum likelihood fit in the dijet mass, excluding of course the signal region for background normalization. And then that was used as an input to L nu JJ mass, which is now shown on the bottom, which was used one for, of course, getting the shape of the background, but also for getting the exclusion limit. And the exclusion limit is now shown on the bottom left, which is quite good. 170 to 180 GeV, and then from 230 GeV to 545 GeV in the entire data set. So again, the limit evolution as one goes in luminosity. So I'm skipping this, but this is the important plot which came in the paper. This was the full luminosity of Run2, 5.1 femto1 inverse and 19.7 femto1 inverse. And here you can see the importance of these 2L2 nu, 2L2 tau, and L nu QQ analysis. 2L2 nu is the most sensitive analysis in the entire high mass range, as you can see, almost entire one. 2L2 tau was, as I mentioned earlier, was supplementing, so it's a green color. This was 2L2 tau, but this was supplementing this 4L analysis quite well. And then this L nu QQ is the blue one, as you can see here. So all of these went into the final combination, which allowed basically the CMS experiment to exclude the existence of this standard model Higgs boson in the entire high mass range. And the expected and the observed one for the individual WW and the ZZ channels are shown on the right one. So next, now I'm going to the analysis related with the associated production. Remember, these production mechanisms have relatively lower production cross sections, but again we have standard handles. So here this analysis where the WH was done with H decaying to WW, or actually to tau tau as well, with 3 leptons. So now coming from these 3 Ws, and you have a missing energy system. So again, analysis was done from the starting and actually was taken up to the full luminosity. So both Higgs to WW and Higgs to tau tau were considered. Now, major background processes again, now in this case comes from WZ and ZZ to 4L, and of course the background coming from the fake leptons. Now, this analysis, if you look into it, to improve upon the sensitivity, was done in the opposite sign, same flavor leptons and the same sign, same flavor leptons. So even though the concentration or the fraction of the same sign, same flavor final state is only 1/4 of the total, but background is actually coming only from the top, because we are considering same sign. So all the backgrounds having this Z and WZ, they basically got reduced. So of course, two approaches were used, cut based and the shape based, as used earlier. So event selection was basically similar to the earlier one, where the leptons were selected, except that now there are 3 leptons, one coming from the Higgs decay and another was this W. So total charge of the 3 leptons are now have to be consistent with ±1. And in this analysis, the minimum of the transverse missing energy and the track transverse missing energy, which was basically from all the charged tracks, they were used. That was used to separate, I mean, to have in the event selection. Again, the top removal, non-BTEC ones, the discriminant which was used, I mean, the final one was delta R dilepton, which was put less than 2 in the cut-based one, and which was used as a distribution for the shape-based analysis. Now, on the left-hand side, I'm showing 8 TeV events with same sign, same flavor. Right-hand side, 8 TeV with opposite side, same flavor. And as you can see that it is the WZ background plus these W plus J, top and W plus jets, which were basically dominating the entire spectrum. But yeah, as I mentioned earlier, the same sign, same flavor, that was more sensitive, even though it was having lesser fraction. You can see the same result for the minimum of those ETMS for the OSSF channel as well. Now, again, this is important because this analysis was done in the low mass range as well. However, the sensitivity was such that even with the full luminosity, the observed limit was 3.7 times the standard model one, and hence it was difficult to conclude anything on the presence or the exclusion of the Higgs at 125 GeV. Delta R is just shown as a distribution here because this was used in the shape-based analysis. So shape-based analysis had a slightly better limit in both in terms of the expectation, of course, 3 and the observed one. Another analysis which was done in WH, again, it's not an easy analysis, where the Higgs was decaying to di tau. Now, this analysis was actually added with this ZH analysis, where Z decays to dilepton, and hence you can understand that the final states in these analyses, I mean, the WH, where we have one lepton, which is coming from W, and Higgs decaying to 2 taus, but one of the tau decays leptonically, or both the taus decaying hadronically. So L tau H and L tau H tau H. Then, of course, we have this ZH, where you have the dilepton, and then from the Z, and of course, the E mu tau, depending on the tau decays, coming from this Higgs decays to tau pairs. Now, backgrounds are the reducible WZ and the ZZ, and then the reducible backgrounds coming from this one. So if I concentrate on the left-hand side, I mean the LL tau H, it's the selection which has to be consistent with the leptons. You have 2 leptons here. So PT of the leptons, then we have 1 taus. Same charge for E mu to reduce this Z background. I mean, if you remember, the WH has this E mu pair. So this was done for the same charge. Veto on additional E or mu to take care of backgrounds coming from dibosons. BJet veto to take care of TT bar. And then scalar sum of ET of lepton candidates, which from the reducible background is kind of softer as compared to the signal. So this was put as an event selection. In the L tau H, again, now here the hadronically decaying taus are there. So you have the single muon or the E plus tau H trigger. And the isolation on two of those hadronically decaying taus were put separately, actually. I mean, the tight ones or the medium ones, depending on the isolation muon or the electron rejection. Transverse missing energy is greater than 20 GeV. Other than that, BJ tweet was there. Veton additional lepton was also there. But in order to take care of the other backgrounds coming from Z to tau tau, there were some additional requirements, which was posed, and also a requirement of MEE to take care of Z to EE background. So without going into this ZH background, I would just like to show what was the visible mass spectrum of the invariant visible mass of the di-tau pairs. You can see that the reducible background constitutes here, but it's the WZ background in the LL tau H channel, and on the extreme right, it is L tau H ones. Now, you can see the number of events there in L tau H category, of course, was lower than the LL tau H. So in this one, L tau H, we had the cut and count based analysis, basically. And on the other hand, in LL tau H, it was the shape based analysis which was performed. Now here is now shown basically the expectation and the observed upper limit. So left hand side again LL tau H. Now in the middle plot it is L tau H. You can see in the entire range 110 to 150 GeV. The combined upper limit was given from all the three channels turned out to be 2.9 to 4.6 times the standard model. If you look at the observed limit here and just compare it with the expected limit. So what was done later on to check if you inject 125 GeV Higgs, standard model Higgs boson signal, and then you look at the consistency with the observed limit, it was found that observed limit was statistically compatible with both the absence and the presence because of the limited statistics here. But this was another good result coming from the low mass region analysis. Now, I'll come to before invisible Higgs decay, I'm coming to the constraining Higgs boson width. It's basically the properties in some sense. Once the Higgs boson or Higgs boson was discovered, you have to think about the properties. So this was constraining Higgs boson width using Higgs to ZZ to 4L plus 2L 2 nu channel. This was quite interesting because what I remember that the theory was also getting developed around the time, and it was the 2013 paper. Remember the discovery took place in 2012. We are constraining the Higgs boson width using with ZZ production. So these papers just came around that time, theoretically, and experiments of course took note of that and immediately worked into it. So the motivation came from the point that the direct measurement of the upper limit on this width of the Higgs was limited by the instrumental resolution. Around in 125 GeV standard model, and the predicted one is 4.1 MeV, or the expected one is 4.1 MeV, whereas the actually direct measurement limits were 3.4 GeV, so orders of magnitude higher in both the golden channels. So what was proposed was this, that there is a sizable off-shell production of Higgs boson, which is of course not on shell but off shell, to constrain the natural width. So there was this cross section which is coming from the on shell analysis, and then there should be cross section coming from the off shell. And if you noted that this gamma H factor, which is the width of the Higgs boson, came only in the on shell one. So that can help you such that the relative off shell and on shell contribution in the channel Higgs to ZZ, for example, can provide limits on this Higgs boson width. Now, of course, there are assumptions that the off-shell decay have the same coupling as the on-shell ones. So those were there, but it was still very nice theoretical proposition and was quickly done in experiment. So in the high mass region, since 2L 2 nu was very sensitive, so this was added to 4-lepton channel. 4-lepton channel was used for the on-shell, and then 2L 2 nu and 4L was used for the off shell for the relative contributions. So in this, basically the 2L 2 nu, I mean, the work was done mainly on the 2L 2 nu from the analyst side. However, the basic selection procedure was same as was done for the earlier one, 2L 2 nu, which was shown. What was done afterwards, that there was a simultaneous unbinned maximum likelihood of a signal plus background model to the measured distribution in both the 4-lepton and 2L2. Each event was put or given some probability, or the probability distribution function was made for on-shell contribution as well as for off-shell contribution, for the signal, for the background, and the interference between the two contributions. Remember, we have the same initial state and the final state between the ZZ and the blown contribution, if you think of it. Then, so this probability distribution was then converted into likelihood, fit was made, and the three parameters, width and the signal strength modifiers for the glue and the VBF, they were left unconstrained. So what I'm showing on the right hand side, bottom plot, the top plot was the transverse mass in the 2L2 nu. You look at the, maroonish line, deep red line, 4L observed and 4L expected, which is shown here. So we have to just look at the 95% confidence level, and let's just see where it is cutting this line. So you see that if you just use the on-shell 4L and off-shell 4L also, the limits were placed somewhere here. If you use on-shell 4L and off-shell 2L2 nu only, then the limits are there for the red. So the two red lines are basically showing that. But if you combine the two channels, then there is this better limit, which I can show you here and which is written here also. So observed limit turned out to be 33 MeV. The expected one turned out to be 42 MeV at 95% confidence level. Remember, if you compare it with the earlier direct width coming from the on-shell measurement, these are order of magnitudes better in this. And with the combination of 2L2 nu, this turned out to be 22 MeV and 33 MeV. Those of you may be aware that this on-shell and off-shell production, I mean, this analysis in the latest era is also submitted to Nature Physics. But this was, of course, the one which I am showing here is only for the Run1 data. Now, if you can do it in the Higgs to ZZ, you can, of course, use the Higgs to WW to L2 nu also. Here, you have to just think about the on-shell and the off-shell region. That is what you have to divide. Although there is a worse mass resolution, but at the same time, larger branching fraction. So the capabilities come from here. Again, I mean, different flavor dilepton final state was considered. So only EMU state was considered in this one. Glue and VBF production was considered. So the event selection, they were basically consistent with what we were doing earlier for the Higgs to WW to 2L2 new ones. It is done in the VBF topology. In general, this analysis, I mean, remember the VBF one has rapidity gap which is greater than 2.5, and I mean large rapidity gap between the jets, high invariant mass, central jet veto. So it basically utilizes that. And then the on-shell and the off-shell distribution was basically, or the region was defined. The analysis was very similar to ZZ, except that since we have a lot of background, so one will have to take care of that. In the on-shell Higgs, it is the transverse mass of the Higgs, which is coming from the dilepton system, and the transverse missing energy, and the dilepton invariant mass. So there are these two. In the off-shell, there was this BDT which was trained using several input variables to basically take care of the background. After that, it was similar that you have to basically categorize each event as the signal-like or the background-like or the interference-like, now defined in terms of these variables for the on-shell and the off-shell, and then a bin likelihood fit has to be performed. So this is what we got. I mean, if you look at the WW limit, the limit plots, the scan is shown only as a function of the Higgs boson width and not the mu GGF or mu VBF. But if you look into that, the WW limit is basically alone was coming out to be 26 MeV observed and 66 MeV expected. And this was shown, this is shown as the red line. The blue line, which corresponds to the ZZ limit. And if you just add the two, the black one, it turned out to be 13 MeV upper limit on the Higgs boson width. So it's quite nice to see that as soon as the experiment started looking for these, the discovered is standard model Higgs boson properties, there was this theoretical development which allowed one to use in the experiments and constrain the width pretty quickly. So Okay, now
Sorry
how
to
much?
disturb you. We have about 2 to 3 minutes left. You can.
Sorry. So I will try to wrap up a little bit faster. Yeah, I mean, few slides, but let's try to wrap up. So invisible Higgs decays, basically the production mechanism here, which you have to have some sort of recoil against some other particle. So it is generally done in the ZH production mode. However, in this analysis where the Indian contribution is there, it is done in the vector boson fusion one. And the motivation comes from the point that we have higher cross section in the VBF as compared to this ZH, and hence greater sensitivity to the invisible decays of the Higgs. So since it's the invisible decay of the Higgs and in the VBF, so we are looking for two quark jets separated by large rapidity gap in high invariant mass and central jet veto, things like those. And of course, high missing transverse energy. So this is the event selection. I'm not going to go into that, but yes, I mean, it has to be consistent with this VBF production mode with large transverse energy, missing energy. And this delta phi JJ has to be less than 1 also in this one. So, okay, I'm just coming directly to the results. Here, the background again, the data-driven background estimation was done. We have Z mu mu data to take care of the Z mu nu, and then accounting for these cross sections and efficiencies. W E nu and W mu nu for the single lepton control samples. It was done in detail, and then the right hand plot, which is the dijet invariant mass and the transverse missing energy, that shows basically that the V plus jets contribution and the TT contribution, I mean, it is dominated by the V plus jets. That of course you can look here as well. Total background turned out to be 339, which was consistent with observed 390 within the uncertainties. Remember, the expected signal events was of the order of 208 for 100% invisible branching ratio. Now, this allowed one to put a limit on the invisible branching fraction, which was done earlier by the direct ones. And here now it is done from this VBF channel. So VBF channel alone was able to put a limit on the invisible branching fraction of the order of 69%, which is observed limit, and expected was 53%. I mean, you can basically see it from here. And when combined with this ZH channel, which is the associated production, the observed limit is 58% or 0.58, and the expected limit is 0.44. So this is the kind of limit on the invisible branching fraction. Remember, if there is a null result in this, it is consistent with the presence of only standard model Higgs boson. So in some sense, this analysis also helped me. I mean, so this is why I put it here. So null result would just indicate a standard model Higgs boson. So now coming to the properties, okay, I will just quickly go into it because most of the analyst actually worked on the combination portion. The mass was measured in the gamma gamma and ZZ channel, and it was supposed to be, of course, now put together. The 68% contours were made for this, again, the production cross section times the branching ratio normalized to standard model cross section. And this is the mass. I'm not going to talk about the limit on the width. That was already discussed actually. But if you look at the direct upper limit, it was 1.7 GeV. Again, order of magnitude higher. The consistency of the best fit sigma over sigma SM for all the channels. Just to see that earlier there was this interesting thing which was happening in the TTH. I mean, tag that those events having associated production with top seem to have larger signal strength modifier. Then there were these coupling modifiers, basically the scale factors with respect to the standard model that expected to be 1, and basically they are all fine within uncertainties. The branching ratio for the BSM which was done is consistent with 0, and then this was the famous plot which was done for this Run1 data, basically for coupling with the bosons and the fermions all put together on the same plot. So yeah, interesting one. This is basically the last one, and I mean, okay, the analysis is very important. It's just that due to paucity of time, I am not going to explain a lot. However, this is the measurement of the differential cross section with the data in the diphoton decay channel. Now, what I'm showing here is, for example, the differential cross-section for PT of the diphoton, rapidity of the diphoton, delta phi, and cos theta star in the Collins-Soper frame. Now, why these are becoming important? I mean, if you just look into it, they are sensitive to higher order corrections in perturbative QCD, for example, this PT gamma gamma. The rapidity plot is sensitive to proton PDF as well as to the production one. The one which is shown below is cos theta star, that is sensitive to the spin of the Higgs boson. So once you gather sufficient statistics, you will be able to make a distinction between the models, which was considered, for example, Harris, Pauheg, and then with different, I mean, this XH was contribution from all other production mechanisms, and it was also done within the effective field theory mechanism. I mean, if you look into it, this is the Wilson coefficient for sixth dimension one. But anyway, the whole idea is that this kind of analysis can be extremely useful in constraining theory. So this is basically it for this one, even though there are other plots for as a function of jets, etc. And I am just going to stop here. That tried to basically give you a flavor of so many things which happened around Run1, and it was exciting to compile it all here. So thank you, folks. That's it.
Okay, thank you, Kirti, for excellent review of all the effort Indians have put in the Higgs search using Run1 data. The floor is now open for questions. Please raise your hands or type in the chat. We can take a few questions before the next one.
Hi, I have a question. Can I go?
Sure,
yes.
Please.
Okay, in slide number 6 or 7, so there is a table of the number of events for the various Higgs mass hypothesis. I mean, 200 GeV or 250 GeV.
No, this one.
Yeah, so if you can check the numbers, you can see that after 200 GeV and in the mass of the 250 GeV, there is a, I mean, loss of number of events if you check any of the channels. So if we know that from the 200 to 250 GeV and the electrons which are coming from that Higgs bosons should be reconstructed samely, I mean, the number of events should not be that different. So is there any proper reason for that? So why the number?
No, I doubt. I mean, this was, remember, it's a low statistics analysis. It is done, if you look into it, all the bills are having, I mean, the ones which are even populated, they are having almost one event. And you are expecting backgrounds which are, again, I mean, if you just think about the statistical uncertainty alone there, that is, I doubt that there was any other interpretation other than that we will have to keep an eye on this p-value in any of the region, wherever we are observing. So this p-value was just being focused for the events where there was excess. For the ones where we are having less events, where it is just about figuring out if the background is properly done or not, or if the channel is sensitive enough. So 4L channel was supposed to be supplemented with some other channels in order to come up with it. Yeah. So this was just a statistical fluctuation to, in my understanding. And it's only the excess which was basically looked at closely, and the backgrounds were checked with multiple ways also. So am I trying to answer it? Because it is only about the statistical fluctuation. That is what I want to emphasize.
Kirti, do you have the plot for the branching ratio? So if the Higgs mass is around 200 GeV or so, it is causing.
Yeah, I got
Yeah.
that, yeah.
So so there.
Okay.
Okay.
Yes, so there is a slight, I mean, loss for the branching ratio from 200 to 250. Yeah, this also matters. Yeah, thanks.
Kanjuri, you had a question?
No, I wanted to comment about this only.
Okay. Yes, please go ahead.
Yeah, okay. So can you go back to that slide, which is the last one before the summary slide?
Oh, yeah. Differential cross section.
Differential cross section of that as a function of diphoton.
Yes. Yes,
So
yes.
the lowest bin has a better statistics just beside that.
The-
There are,
This
yeah,
one?
the lowest PT has the better
No, no,
statistics.
it's added, it's the sum. Some of the bins which are not overflow bin.
Okay, overflow bin. Okay.
Okay. The ones which is here, I mean, are you talking about the overflow here or?
No,
Yeah.
low end. I was surprised
Which
at the low end because that has a lower error than the one to beside it. Okay, I understand.
Right.
Yeah, because these two basically,
PT diphoton, right?
In lower side, there is no overflow.
There is no, I
There
thought-
won't be any underflow here. The overflow bin only is here. So that's why I just got confused. What have you understood there? I'm not sure.
two errors which are basically close to how much 20 and 40. These have higher errors than the lowest one, which is close to 0.
Right.
It is around
Row. So
Yeah, but I mean, my understanding it is what you are seeing is basically the statistical fluctuations,
one. Okay.
which is I mean, downward in the log plot is looking like as if it is a big one. But if you look into it, these are not very different on the logarithmic plot. I mean, I hope you understand the sentence which I'm trying to make.
Okay. Okay.
Hi, this is Prolay. Can I comment?
Yeah.
Yeah, I think I mean this is the 8 TV result. You have to understand with the grain of salt that this is Higgs PT there, and I have forgotten where was the average PT of the Higgs. I think it suffers from the statistics, below 50 dB or so.
Yeah, you can see it in the log plot, I guess. Yep.
Yeah.
Thanks, Arpal.
Are there any further questions or comments? I don't see any. Thank you, Kirti, for an excellent review. Thanks again. Nice seeing you after a long time.
Yeah, thanks a lot. Pleasure is on mine.